Hey guys, welcome back to Computational Biology with Python. We're going to continue in this video working with our seq objects and learning all the things that we can do with the seq package to manipulate sequences. So let's just jump right back into it. Where we added two strings together. We're going to continue to manipulate strings. So let's do contigs equals seq. Let's do an ATG, and then we're going to do seq ATCCCG. You can do whatever, actually. These are the ones that I'm doing. And then seq TTGCA. And then let's do spacer equals seq. I'm going to say n. I'm going to say times 10. So if you ever have gotten sequences for MCBI, or if you've had sequences run from on Illumina or anything like that, an n is where the sequencer was not confident enough to determine what the nucleotide was. So it could be any of the four, right? So if this usually happens when you get to the end of long reads, so like at the tails, there'll be a lot of n's because the fidelity of the molecular machine that is doing this, it goes down and it's no longer able to tell what it is. So now we can use this join function, spacer, join, contigs. So how do we spell contigs? With G in it. So we're saying, okay, take the spacer object that we made, these n's, and then we say join with the contigs. And so as you can see, what it does is it joins in between. It puts the 10 n's in between each one. So it uses it to join them together. What else can we do with this? We can do, sometimes you'll get a sequence where, DNA seq, where you need case sensitive stuff, so ACGT, ACGT. Like say you're trying to blast a sequence or do something and your database is all uppercase but yours is lowercase and whatever program you're using is case sensitive, well, that's gonna be a problem. So what you can do is, let's print it real quick to see, make sure we got it right. Good. You can do DNA seq, DNA seq, and then say upper, and we'll make sure that everything is uppercase. Or we can do DNA seq lower, and we'll convert everything to lowercase. So that's very useful to manipulate these strings instead of going through everything and changing each one, just one little line of text. All right, so what about matching? What if we want to find, so we have, actually I'm gonna convert it, let's convert it back to upper for this, DNA seq dot upper, because that's usually what we use. Okay, so what if we want to search for like you could search for like a start codon, which we don't have in this, but we'll do, well, actually, let's search like this. So we'll do GTAC in DNA seq. And as you can see, it says false, even though we have a GTAC because it's case sensitive, right? So if we do GTAC in DNA seq, it'll say, oops, cancel. It'll say, wait, Why is that saying false? Let's see, why is that? DNA seq. Oh, because we didn't save it. So we have to do this. DNA seq upper. Okay, so we have to save it as that variable. So now if we run GTA TAC in DNA seq, we should get true. There we go. In our last course, or a few videos ago if you're watching on YouTube, we made a script in Python to convert or do transcription and translation for a FASTA file. Of course, this is something that's common, so there's already a Biopython thing for it. So we'll do my seq equals seq. We'll do, just make up some letters, as long as you have, make sure it's all nucleotides. All right, so this is my seq. And now, if I do my seq complement, you get the reverse complement, right? So G's pairs with C's, A's pairs with T's. So that's very nice and conserve. So this is just the complement. But if you want the reverse complement, so in the opposite direction in reverse, so it's essentially taking this, giving the complement, and then doing the -1 thing where we reversed it. You do my seq reverse complement, and if we run that, you get the reverse. So it starts over here. It's going backwards. So yeah, I just explained. We won't do the example, but I just explained that it's doing the reverse and using the -1 together. All right, what about if we want protein sequence? So let's do protein seq equals seq, or if we want to work with protein sequences, EV RNAK. And then we do protein seq complement. You can get the, oops. Oh. Let's try now. You can get the complement for that. And you have to remember though, we get the complement for it, but it's biologically meaningless, right? So there's no at that point of doing like a reverse complement, you have to be careful because it doesn't make sense to do reverse complement of a protein sequence because protein sequences are a finished product, right? And so, well, I shouldn't say that. Biochemists would kill me for saying that. Protein sequences are done with the RNA part of translation. So there's no reversing them or finding the reverse. It doesn't make sense to do it. But you can do it in Python. So that's something that you have to be mindful of and be careful of, that you're not accidentally, if you're looking at, forward and reverse strands or whatever, and you don't translate them before you do the forward and reverse. Because Python will go ahead and do it for you, but it doesn't make sense to do. Okay. So what does this mean? What's happening is that and if we look at the complement, So E complements E, V complements B, Y complements, like where is it getting these things from? Well, it's because there is this ambiguity code for nucleotides. So kind of like N can mean any nucleotide. V can mean, V means A, C, or G. B, and its complement is B. All right, I'm not gonna get too much into it. Anyways, these are ambiguity codes, and so like, all it's saying, if you see a V in a sequence, it could be A, C, or G. And so what's happening is when we do this protein sequence complement, it's taking these letters and it's thinking that they're these ambiguity codes. Anyways, all right, let's keep going. So one thing, yeah, we'll just keep weeding some stuff out here. All right, so let's create a code. Seek. Okay, so let's run this, and then we show our coding DNA so that we have our sequence there. Perfect. Now let's create one called a new variable called template DNA, and we'll call this coding DNA reverse complement. So now we have the reverse complement, which is generally how transcription works. And now let's transcribe it. So we did this before, right? The translation with the reverse complement, but now let's transcribe it into, or translate it into a protein. So what we do is so we have, okay. Okay, so one thing is so essentially Python takes a shortcut when doing transcription. Let's go over this first. So coding DNA, you see that we have, ATG, blah, 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 blah. And so our messenger RNA equals our coding DNA, and then transcribe. So that, and then we got to call messenger RNA. And so as you can see, all it's done is it's taken our sequence and it's taken T's and converted them to U's, right? But if you wanted to do, so our coding DNA was our mRNA, right, or our RNA, right? Or the part that's being coded. It wasn't turned into RNA because it didn't have any use. But if you wanted to do biological transcription, starting with like a template strand, then it becomes a two-step process, right? So template DNA, so not the coding DNA, it's our template DNA. So this is just the raw DNA sequence on the chromosome. Reverse complement transcribe. And we should get the same thing, right? So what's happening is it depends on if we are, so our coding DNA here is our actual RNA molecule. And then we just replace the T's with U's to get our actual RNA, right? Because thymine doesn't exist in RNA. But for the biological process, when you see transcription, the transcription machinery come in, it reads the template, right? So first it reads this and creates the coding DNA, and thus the messenger RNA, if that makes sense. So the transcribe, so by using the coding DNA, we are essentially enacting kind of a shortcut. It's only one step. Okay, let's see. Oh, another thing you can do is you can do reverse transcription. So let's do messenger RNA. So this is our, actually we already have messenger RNA, right? Yeah, so let's use this messenger RNA. So messenger RNA, and we can do messenger RNA, and then we can say back, transcribe, and it gives us back and forth, right, between transcribe and back transcribe. So you can take a piece of DNA, the coding piece of DNA, and you can turn it into RNA with the transcribe function, and you can turn it back into the original DNA by doing back transcribe, which is reverse transcription. Right. So what else? What are we at? 18 minutes. All right, let's do one more. Let's translate quick, and then we'll cut this video. Okay, so we have our messenger RNA, and easy enough for us to transcribe it. We can do messenger RNA, or sorry, translate. I've been messing this video. I apologize for any confusion this video has caused. All right, translate. So transcription, take DNA, make it into RNA, right? Replace the U's with T's. Bingo. RNA then goes to the ribosome outside the nucleus. Ribosome then looks at these codons, groups of threes, and it says, okay, this is the next amino acid that needs to be incorporated into the growing chain for this protein. Translation, that's called translation, not transcription. If I've messed up because I'm trying to code and explain biology, I apologize. So we're translating. RNA is turning into protein. Okay, it's easy enough here with this translate function here. So why do we have 2 asterisks? Well, those asterisks are stop codons. So that's where we no longer have protein being added to the sequence. So this was, in my case here, the sequence was deliberately chosen so we could show that you can have multiple stop codons. So this would be the protein, because at this point the ribosome says nope, and we're going to continue. We're going to not add these last 4 amino acids. So the nice thing too, we can do. Wait, hold on. We're gonna stop. I said we were gonna stop before, right? Yep. All right. So we're gonna stop right here. Process, don't really take too much stock in it. It's not a big deal. Just use the translate function for your coding sequence, not your template sequence, and you're going to be good to go. Thanks for watching. If you're watching on YouTube, please hit like, please hit subscribe, tell your friends.